All right. So now that we've reminded ourselves a little bit about complex numbers, we can tie them together or tie them into trig. So the way that we tie complex numbers into trig is we look at their polar form. And we don't just do this for fun. We do this because it turns out to be very, very useful for certain things, which we'll see in 8.3 and 8.4. Okay, but for now, we're just going to practice a little bit of writing. Sorry, I have to adjust it because it keeps going in and out of focus. But for now, we're just going to try to learn about writing polar numbers or complex numbers in polar form. Holy schmoly. There we go. Hopefully, if I pass my hand in front of it, it doesn't go blurry. No, it does. It's still. I don't know why it's doing that. Anyway, but let's get to it. So first of all, if you have some complex number like a plus bi can be graphed in the complex plane. So for example, the number 2 minus 3i. We can represent that in the complex plane. The complex plane is formed by basically treating this number as the ordered pair 2, negative 3. So the y-axis becomes the imaginary axis, and the x-axis becomes the real axis. And those are the standard kind of abbreviations that are used, but so 2 minus 3i would be that number right there. Okay, so, and in fact, that's a really good way to think about complex numbers, is that they're just two-dimensional numbers. Whereas real numbers are one-dimensional, non-real complex numbers are two-dimensional. So anyway, now one thing that we can tie together with this pretty immediately is that these complex numbers then can be thought of as vectors. Okay, so you may note that a plus bi corresponds to vector ab. When we think of complex numbers this way, it's totally consistent with what we know about both vectors and complex numbers. For example, if you had the complex number 4 plus I and you wanted to add the complex number 1 plus 3i to it, then we said in 8.1 that the way you would do this is you would just combine like terms. So you would say 4 plus 1 is 5, and I plus 3i is 4i. Well, when we were talking about vectors, we said if you had the vector 4, 1, and you wanted to add the vector 1, 3, well, then you would just add like components. And again, in this case, you would get the vector 5, 4. So it's really the same idea. And that idea even works out geometrically. So geometrically, here's the complex number 4 plus I is right there. We can think of it like the vector 4, 1. Here's the complex number 1 plus 3i, and we can think of it as the vector 1 plus 3. And now if you're thinking about what the resultant of those two vectors should be, geometrically, you would make a little parallelogram, and the resultant would be the diagonal of those vectors. Well, where does that point end up? Well, it just so happens to end up at 5, 4. 5 plus 4i, vector 5, 4, right? So all of these concepts match up when we treat complex numbers like vectors. So what does that have to do with polar form? Well, to write a complex number in polar form basically just means to rewrite the complex number in terms of the magnitude and direction angle of its corresponding vector. Okay, so you think of the complex number like a vector, you find the magnitude of the vector, and then you find the direction angle of the vector, and then you can rewrite the complex number in terms of that magnitude and direction angle. As far as vocabulary is concerned, instead of magnitude, when we're dealing with complex numbers, instead of calling it magnitude, we're going to call it the modulus. So magnitude of a complex number, we would really call that the modulus of the complex number, but it corresponds to the magnitude of the corresponding vector. And instead of direction angle, instead of the direction angle, we're going to use the term argument. So the argument of a complex number is just the direction angle of its corresponding vector. Okay. Anyway, so we can write these complex numbers in terms of their horizontal and vertical components. So our goal basically, is to rewrite the complex number x plus yi in the form r times cosine theta plus I times sine theta, where r is the square root of x squared plus y squared, right? It's just the magnitude of the vector, or in other words, the modulus of the complex number. So r is x squared plus y squared, and tangent theta is y over x. So it's just the direction angle of the vector, or the argument of the complex number. Okay? So I'll give you a couple examples of this. Was there something I wanted to say first? I think that's it. So let me just walk you through, I'm going to walk you through 4 examples, writing something that's given to you in rectangular form and rewriting it in polar form. Oh, I remember the thing I wanted to say. We sometimes use a shorthand notation for this. Instead of writing out r times cosine theta plus I sine theta, we sometimes just call this r cis theta. Or maybe r kiss theta. Sounds kind of nice. And since it's cosine, it's a hard C anyway. So maybe we should say r kiss theta. But I think most people say r cis theta. Anyway, this is how I usually write it, which is why I was stumbling a little bit when I first wrote this down. Anyway, let's look at a couple examples. More than a couple. We'll look at 4 examples. So let's rewrite in polar form. By the way, polar form is sometimes called trigonometric form. So the trigonometric form of the complex number. I use the word polar because it's easier to say. So let's do polar form. Polar is a very common term for it too, though. So in polar form, let's do 1 plus I times the square root of 3. Okay, I'll walk you through one from beginning to end so that you can see how it goes, and then I'll give you another one to try on your own. Okay, but if I want to write this thing in polar form, the first thing I would do is graph it so I have some feeling for what quadrant we're going to be in. And that's important because when you're trying to find the direction angle, remember when we were doing this with vectors, sometimes when you just take tangent inverse, you end up in the wrong quadrant and you have to adjust things a little bit so that you end up where you're supposed to be. So it's important to get a graph so that you know where you are. In this case, we have 1 plus root 3. Root 3 is like 1.7, so it's somewhere between 1 and 2. So there's that complex number. So we're in quadrant 1. So in this particular example, we'll just be able to take tangent inverse up here when we're trying to find the direction angle, and it'll put us in the correct quadrant. Okay. Okay. So first of all, we need to find r, right? The magnitude of the vector, or in other words, the modulus of the complex number. So r is going to be x squared plus y squared. That's 1 squared plus root 3 squared. That's the square root of 1 plus 3, which is the square root of 4, which is 2. Okay, so r equals 2. And then we need to find the argument, or in other words, the direction angle. Okay, so tangent theta is y over x. So tangent theta is root 3 over 1. So that means that theta is tangent inverse of root 3. You could plug that into your calculator, or you could work it out in your head, right? You know that tangent is sine over cosine. So basically you're looking for where sine is root 3 over 2. And sine is root 3 over 2 at 60 degrees. Okay, so this would be 60 degrees. Or in radians, if you were working in radians, it would be pi over 3 radians, right? So we could say 60 degrees, or, you know, pi over 3 radians. I'm not sure. I think on some of the problems, the textbook will put the answer in radians, and on other ones, it'll put the answer in degrees. I mean, just follow kind of the format that the book takes. But we'll do it both ways here, just so that you see it. But okay, so theta is 60 degrees or pi over 3 radians. And now we can give our answer. So in polar form, 1 plus I root 3 is going to be r, which is 2. Maybe I'll write it out. R is going to be r cis theta. So that's going to be 2 cis 60 degrees. Right? Or you could say 2 cis pi over 3. Either one of those would be a good answer. Okay, so that's that one. Here's another one for you to work on. So go ahead and give the video a pause and see if you can do this one. See if you can change -2 plus 2y and rewrite it in trig form or polar form. So give the video a pause, see if you can do that. Here I go. So first of all, a notation that I'm not sure if the book's going to use this notation, but it's pretty common to call polar numbers z. So I'm just going to say that this thing equals z. And now I can do the same thing I did before. So I'm going to start off by plotting z in the complex plane. So that's going to be -2 plus 2y. That puts me in quadrant 2. Okay. Now I'm going to find r. Okay, so r is 2 root 2. Then I'm going to find theta. Okay, now if you take tangent inverse, right, so you'd say if you take tangent inverse of -1, you're going to get -45 degrees. Okay, so if you plug that into your calculator, you'll get -45 degrees, which puts you in quadrant 4. That's not where you want to be. You want to be in quadrant 2. So you want the angle that lives in quadrant 2 who has a reference angle of 45 degrees. Okay, so another way to get there is to just take -45 degrees, add 180 to it, right? So what do you get when you do that? So if I add 180 minus 45, so 135, right? So theta is 135. So I'm going to say plus 180 so that we end up in the correct quadrant. And that's 135 degrees. What would that be in radians? Oh, we'd be at 3 pi over 4 radians, right? So, or theta equals 3 pi over 4. Okay, so to give our answer, we're going to say, all right, so z equals r cis theta. Or in polar form, you'd say z equals r cis theta. Okay, either one of those. Okay, let's do another one. We'll do a couple of kind of simple ones, but sometimes the simple ones throw us off more than the challenging ones. So let's try negative 2i. Let's see if we can write that in polar form. Go ahead and give the video a pause and see if you can work it out. Okay, now here's my solution. So negative 2i, this is really like 0 minus 2i. So the real part is 0, and then the imaginary part is negative 2. So there's that complex number right there. So you can stick with the strategy that we did before, but it's going to be a little bit of overkill because it's a little more obvious than that. So let me just show you. If you do this the long way, you would say r is the square root of 0 squared plus negative 2 squared. That's going to be the square root of 4, which is 2. But of course, that should have been fairly obvious, right? Because if I call this number z, then pretty clearly the absolute value of z, or in other words, the modulus of z, is going to be 2, right? It's the length of this vector. This vector clearly has length 2, right? So the absolute value is 2. The modulus is 2. Anyway, nothing wrong with doing it the wrong way, or nothing wrong with doing it the long way. But you can maybe save yourself a little bit of effort if you just think it through and if you understand conceptually like what these things represent. So there's the modulus. Now for the direction angle, same thing. The direction angle is 270 degrees. You can tell that just looking at the picture. If you were to do it the long way and say, all right, well, tan theta is y over x, that means that tan theta is going to be negative 2 over 0. Uh-oh. That means tan theta is undefined. Okay. Well, where is tangent theta undefined? It's undefined at 90 degrees or at 270 degrees, right? Or in radians, it's undefined at pi over 2 or at 3 pi over 2. Well, how do you know which one? You look at the picture, right? Clearly, it's at 3 pi over 2 or 270 degrees. So again, there isn't really any need to even do all of this work. You can look at the picture and kind of tell that theta is going to be 270 degrees here, right? Okay, so in polar form, then we'd say z is r cis theta. That's that. Or you could do it in radian form as well. Okay, one more pretty similar to that. If the last one stumped you, then hopefully this one's a little easier now that you've seen the last one worked out. But let's just see if we can write a real number in polar form. So let's see if we can write the real number 7 in polar form. Go ahead and give the video a pause, see if you can do this. Okay. We draw a picture, right? 1, 2, 3, 4, 5, 6, 7. There's this number. The direction angle is clearly 0, and the modulus is clearly 7. So I'm not even going to do all of the long work. I mean, you could. You're welcome to do it. You're welcome to think of this as 7 plus 0i and go through all of these steps. But where you're going to end up is that well, if I call this number z, where you're going to end up is that z equals 7 cis 0 degrees. I guess I should mention, so let me give you one more, which I'll call D star. But let's say that you had a negative real number like -7. You might be tempted to write this as in polar form as -7 cis 0 degrees. And that's technically not wrong. That does get you in the correct place. But usually we like for our modulus to be given as a positive number. In a similar way, you could say, you know, instead of 0 degrees, you could use 360 degrees. And that would also be correct, but typically we like our angle to be between 0 and 360, not including 360, okay? So in reality, the way that we would describe this, 1, 2, 3, 4, 5, 6, 7, right? So we're out here. What we would really say is that the direction angle is 180 degrees. And that the magnitude or the modulus is +7. So then we'd say -7 is really +7 cis 180. And that would be the way we describe that one. Okay. So that pretty much does it. But let me just give you a couple examples working the other way around. I think it's a little more straightforward going from polar to rectangular form. But just to make sure we're on the same page there, let's look at a couple. So let's rewrite in rectangular form. So this time we're going to be given the complex number in polar form, and we're going to have to rewrite it in rectangular form. So let's do 3 cis 35 degrees. Go ahead and give the video a pause and see if you can do this. Okay, here's my solution. So I'm just going to expand this. I'm going to write this in expanded form. Right? This is 3 times cosine 35 degrees plus I sine 35 degrees. I don't know cosine 35 degrees off the top of my head, so I'm going to have to plug this into my calculator to see what I get. So cosine 35 degrees was about 0.819. Anyway, but I'm going to distribute the 3 as I go. Okay, so I'm going to say this is approximately, 3 times cosine 35. So that's about 2.46 plus 3 times sine 35. That's about 1.72. 1.72 I. Okay. Oops. And one more. Let's do 2 cis pi over 2. So give the video a pause, see if you can work that one out. You should be able to do this one in your head pretty quick. Okay, here's my solution. So this is going to be 2 times cosine pi over 2 plus I times sine pi over 2. Cosine pi over 2 is 0. Sine pi over 2 is 1. So this is, well, if I distribute the 2 times 0 is 0. And if I distribute it here, 2 times 1 is 2. Okay, so in other words, 2i is the answer there. And that's it, right? That's all there is to writing complex numbers in polar form.